What we have done, we have introduced the action for a scalar field in the presence of the linear source, and this action is given by the following expression. So 1 over c d for x, standard kinetic term for a scalar field, then the mass term, and finally a new term which describes interaction of our scalar field with a linear source. Linear source term. Now, if you come back to our discussion of physical dimensions, and if you recall the dimension of the field phi, you can easily deduce the dimension of this source, recalling that dimension of the action is the same as the dimension of h bar of the Planck constant, and dimension of h bar is the same as the dimension of angular momentum. So if you recall all these things, then you will find out that our linear source has the following physical dimension. I will write it in square brackets as usual. So physical dimension of our source turns out to be square root of h bar c. So here I'm writing everything in terms of explicit physical constants, divided by length cubed. And now an interesting thing is that this quantity, square root of h bar c, has the same dimension as an electric charge. So this is the same dimension, I mean physical dimension, as electric charge. So in a sense, what you see is that when you introduce this coupling of an external source with a field phi, this source has a dimension of the density of electric charge. So electric charge per unit volume. Per unit volume would mean the density, and this is what is the physical dimension of this source. Now, as soon as we add up this source, we are changing the energy. So our Hamiltonian receives an extra contribution from this source term. And this extra contribution to the Hamiltonian, I denote Hj, and it will be just given by this term here, but with a minus sign, because this term enters the Lagrangian with a plus, but when I will be deriving the Hamiltonian, by the standard procedure, I will write PQ dot minus Lagrangian, and therefore this term will come into the Hamiltonian with a minus sign. So there will be minus three-dimensional integral or spatial over spatial directions, j on x phi x. So this is extra contribution to the energy coming from interacting of our field with this external source.
Professor?
On the other, yeah.
Here is the scalar field here charged, or it's a real scalar field?
This is a real scalar field, but what I'm talking about here is about a source. So I'm discussing the dimension of a source itself. You can consider also a complex scalar field. There is no big difference, but for me it is just you can consider just a complex scalar field, but for me real scalar field is enough.
Okay, thank you.
Now, what we also see that as soon as we add this source, equations of motion for phi in the presence of this source gets changed. get changed. And so new equations of motion will have the following form. So it's a Klein-Gordon operator, d mu, it's a covariant Klein-Gordon operator, plus mass squared. And all this is acting on phi on x. And if this would be the usual scalar field without a source, then on the right-hand side, we would get 0. And then it would be the usual Klein-Gordon equation. But now this is not 0, but we have j on x. So we have a source term. And now we have to write down a solution of this equation. And solution is given, as we know, by Green's function. So we write solution phi on x as sum prefactor I over h bar c. And then we use the Green's function. So four-dimensional integral of the Green's function g x minus y integrated with the source j on y. And we know that what is the Green's function? Green's function is a solution of the fundamental equation, fundamental Klein-Gordon equation, where on the right-hand side of this equation, we have a delta source, so point-like source, minus I h bar c, four-dimensional delta function, say x minus x prime. So impulse which appears at x equals to x prime, and it is the right-hand side of our equation for our equation which defines for us the Green's function. So now I have to write here the particular g, which is the solution of this equation. So Green's function is a solution of this equation. Of course, we know that there are many solutions of this equation, because to any solution of the inhomogeneous equation, we can add up solution of the homogeneous one. So Green's function is not unique, that we know very well. We have already seen that there are such things as retarded Green's function, advanced Green's function, Feynman propagator. But for us, at the present discussion, does not matter which Green's function you pick up. Pick up any. It's not so essential for my discussion here. Pick up any, then solution will be written by using this Green's function, and then it's trivial to verify that it's indeed a solution. You act with this operator d mu m squared on phi on x. Then this operator gets inside the integral and acts on Green's function d mu plus mu squared acts on g x minus y j on y. So this operator acts with respect to the variable x. Then this is then replaced by the definition of what Green's function is, by minus h bar c, four-dimensional delta function. A four-dimensional delta function here, x minus y. And then you integrate this delta function with the source, and you see that you are exactly reproducing the source term on the right-hand side. So indeed, if you know the Green's function, then you know solution of this inhomogeneous equation. So what is my goal now is to calculate the interaction energy, this quantity here, which is mediated by a scalar field between two equal charge static sources, represented by point-like particles sitting at positions x1 and x2. So what we can have in mind is this picture. So at point x1 in space, we have a point particle, and at point x2, we have another point particle. So these particles are static. So this means that their positions are fixed and they are not changing with the time. So it's like you take one particle in your left hand and another particle in your right hand, and you keep them at a certain distance, and you don't allow them to move. But due to the interaction mediated by a field phi around, these particles will interact with each other. So there will be a force which these particles will exert on each other. In particular, because we will interpret, say, a particle at x2 as a source of the field. So this will be a source. So this will be something which for us generates the scalar field, so produces a scalar field. And this particle, which finds itself under the influence of the scalar field, we will consider this as a test particle. So we have a test particle. So we have a source particle and we have a test particle. Source particle and a test particle. So what does this mean in terms of mathematical formulas? We set up J2, the function depending on x, to be equal to square root of h bar c delta function x minus x2. So this is a, if you wish, a source. We consider this J2 as a source of a scalar field phi on x. This source is point-like and it's static. The source is concentrated at a point x2. You see, when x is equal to x2, then you are on support of this delta function, and the value, the magnitude of this source is proportional to electric charge, to the quantity with the dimension of electric charge, so square root of h bar c. And this is something, when I say that this is a source, it means that I would like to use this J2 in the right-hand side of this equation. So I plug in here, and then the response of this to the presence of this source will be a scalar field phi on x arising in the surrounding space due to the fact that we put this source at a position x2. And so the first particle, on the other hand, will be represented in a similar manner. So we will associate to it a function g1 on x with the same properties. So it will be h bar c delta function x minus x1. So this is test, and this is source. So this means that the energy Hj, which I interpret as an additional contribution V to the energy of field phi due to the interaction of my test particle with the field phi, will be given by minus integral dx j1 on x phi on x. Yeah, so this is the same formula which I had before. This is the same formula here, except now I consider as my test particle a particle concentrated or sitting at the position x1, and it's static. But on the other hand, as I said, since phi on x is a scalar field produced by source J2, I can write for phi an explicit solution in terms of the Green's function. And so then continuing this formula, I will write here minus I divided by h bar c integral dx. Here is a dx, three-dimensional dx, and then I substitute j1 on x And now I substitute a source phi on x, but phi on x is given by the integral with the Green's function. So in fact, here I have to add up this integral. So let me put here also this integration measure, say over the variable y, d for y, j1 on x as before, and then this Green's function gx minus y, j2 on y. So this is our source. Source generates a field. This is a field, and field interacts with a test, which you can also consider as another source. So who is test, who is source? You see, this is interchangeable. This is interchangeable, and you can consider once J2 as a source and J1 as a test, or you can do it other way around. Does not matter. You see actually that the formula which we are writing down here almost completely symmetric with respect to x and y. There is only little difference here for the moment that here integration is 3-dimensional and here integration is 4-dimensional, but you will see in a second that we will reduce this integration also to 3-dimensional integration.
So can you repeat what's HJ here?
Sorry, what is J?
HJ. Is it Hamiltonian due to interaction?
Yes. So HJ is a Hamiltonian, is a contribution to the Hamiltonian from the source, from interaction with J. Okay, and this gives extra energy. So this extra energy I denote by V. It's the same as HA. It's I'm writing as V now because you will see that this V will be just a potential arising between these two static particles. So I'm in fact, mathematically speaking, what I'm doing, or physically speaking, what I'm doing, I'm computing the potential arising between 2 point static particles, interacting with each other by means of the scalar field phi. So phi is a mediator, is a mediator of interactions between these two particles. It mediates interactions.
So does Higgs field work like this way?
Yes. In a way, how I will tell you a little bit later how this was introduced, how this idea of a scalar field mediating interaction between particles was introduced, and why people did this, why people come to this idea. Let me just continue a little bit with an explicit formulas, with an explicit computation, with explicit formulas. So what I will do, I will compute now these integrals rather explicitly by using the knowledge of the Green's function. So first thing I do, I just substitute the expression for these sources. Let me, for simplicity, well, let me also do the following. So here I just introduce a source with a unit value of charge. But if you want arbitrary value, then you may multiply it with a number. So let's multiply each of these sources with a number q. Q is just number, and then q number multiplied by square root of h bar c will have the dimension of electric charge. And then q is, you can consider q arbitrary, but I'm taking these two particles to be charged in the same way. So they carry the same charge. Two particles of the same charge. And then you will have here, upon substituting the point-like sources J1 and J2, you will have the following: minus IQ squared integral dx d for y. Then there will be g on x minus y, Green's function, delta function x minus x1, delta function y minus x2. And then what I will do, I will go to the Fourier representation of the Green's function. I will take as a Green's function a Feynman propagator, the Feynman propagator, but it does not really matter which one you take. As you will see in the moment, that does not really matter. So upon doing this substitution of g as a Fourier integral, you will have the following: so plus q squared h bar c divided by 2 pi in the power of 4, and then there is an integral d x d for y, and now I substitute d k dk0, so 4-dimensional integral, and then Fourier for this Feynman propagator, minus I k0 x0 minus y0, exponential I k x minus y. In the denominator, our famous expression k0 squared minus k squared minus mu squared plus little I epsilon, and then these two delta functions, x minus x1, y minus x2. Okay, so this is this integral over k0 and k vector is our Fourier integral representation of the Feynman propagator, which I have substituted. So this is the same as g represented as such an integral. Now, let's see. First of all, we can integrate over x and y. So this is trivial because then x and y here will be replaced x by x1 and y by x2. Another thing which we can do immediately is to integrate over k0. Because let's see, not over k0, over, I think, over y0. So if you write this measure here as d3y dy0, then you can integrate over y0, because y0 comes only with this exponential here. So this is the only exponential which depends on this variable y0. So I k0 y0, and there is no anywhere y0. And so when you integrate over y0, what you get is essentially the delta function up to proportionality coefficient is a delta function on this variable k0, because you're integrating exponential. Integral of exponential I k0 y0 is just proportional to the delta function. So if I write it, if you allow me, I will write it as you need to take 1 over 2 pi to be exact, and then this integral over dy0 will produce for you just delta function of the variable k0. So this means that we are now arriving to the following expression. So q squared h bar c 2 pi cube, because 1 2 pi will go for the integral here to produce delta on k0. Then we will be left over with a three-dimensional integral over k, and integrals over x and y we say are simple. They will produce for us this exponential I k x1 minus x2, right? And then in the denominator, since we are integrating over k0 and get delta function, we can integrate over k0 with this delta function. So basically k0 will be replaced by 0 in the denominator. And then what will be left over in the denominator, minus k squared minus mu squared plus I epsilon. I epsilon is not really important now because, well, minus, let me take it out and write here k squared plus mu squared minus I epsilon, and this k squared here is only spatial, this spatial square of the spatial momentum. No, because now k0 due to the delta function is 0, and so you have just vector k squared plus mu squared minus I epsilon. But now I epsilon here, you can take a limit epsilon to 0, because this integral has no problem with the denominator, because k squared is non-negative, and there is always positive mu squared added to it. So integrating over k squared will never meet a pole, and therefore you can safely remove I epsilon from the denominator. And that actually shows that you can start from any Green's function, because all these Green's functions differ by the I epsilon prescription. If you write them out in the form of the Fourier integral, they differ from each other only by the way I epsilon enters denominator. But as we see, this integral has no problem now because of special kinematic configuration where k0 is 0. This remaining integral has no problems on the real line, on the real value of this k squared, and therefore we can just remove I epsilon. And so we are left with this integral. Our v takes this nice form, minus q squared h bar c divided by 2 pi cube integral dk exponential ik x1 minus x2 divided by k squared plus mu squared. And this integral we can compute explicitly. This can be done by passing to spherical coordinates very easily. Let's introduce the modulus of vector k. I denote it by k without vector on it. And I will introduce r, the distance between points x1 and x2, which is a modulus x1 minus x2. It's a distance between these 2 points. Then we can choose the spherical coordinate system by directing the axis z along x1 minus x2. And so then our integral will be written in the following way. In spherical coordinates, minus q squared h bar c divided by 2 pi cube. Integral from 0 to infinity. Integration goes with a spherical with a measure of spherical coordinate system. So k squared dk. And then there will be integral from 0 up to pi sine theta d theta. And there will be integral from 0 up to 2 pi d phi. So k squared sine theta d phi, this is a measure, standard measure dk in the spherical coordinate system. No, and then there is a expression which we need to integrate. It's exponential I k r cosine theta divided by k squared, so square of the length of vector k plus mu squared. Also, spherical coordinate system, you can think about this in the following way. So this is direction of x1 minus x2, and this is the same as z direction. Then you have x and y, and then you have our vector k, which is a running vector over which position of which we integrate. No, and then we introduce an angle theta of a spherical coordinate system, and then two angles. So this theta, this phi, two angles, and then there is a modulus of this radius vector, which I denote as simply as k. And the measure, standard measure, dk, is k squared dk sine theta. Oh, maybe let's write it in this way: k squared sine theta dk d theta d phi. Yeah, so I use this measure. So this is how this integral looks like. Now, nothing depends on angle phi, so you can immediately integrate. So you will get just 2 pi from this integral. This is clear. Then you can also integrate angle theta over angle theta. That's because measure sine theta d theta is simply minus d cosine theta, which is very convenient because cosine theta is standing just in this exponential. So you can make a change of variables, making cosine theta a new variable. So that's easy. And then what you will be left over upon making this integral is minus q squared h bar c divided by 2 pi cube. Integral from 0 to infinity k squared dk. This integral we have not yet taken. And from, as I said, integrating over phi and theta, what will be left over is 4 pi divided by kr multiplied with sine kr divided by k squared plus mu squared. So this expression here, sine theta kr in particular, comes out from integrating this exponential here, exponential ika cosine theta. Okay, so r you can take out of the integral and proceed as follows. So what you get is minus q squared h bar c, 4 pi partially cancelled with 2 in the power cube, leaving 2 pi squared. So 1 pi is also cancelled out. R gets out. And then I think what you will have is integral from 0 to infinity dk, 1k cancelled with k squared, leaving k. And so you will be left over with k sine kr divided by k squared plus mu squared. So you get such an integral. And this integral here, I will denote as I depending on r, depending on variable r. So r is standing here, that's why I call it I depending on r. This integral can be computed by using the Cauchy residue theorem. Cauchy residue theorem, this can be done very easily. This, in fact, standard integral you compute in the exercises in the theory of complex variables. So this you can write as minus d over dr, integral from 0 infinity dk cosine kr divided by k squared plus mu squared. So you see, when you differentiate cosine, k will come out and cosine will turn into sine, and then you get exactly this term here, k sine kr. So you can write this as a derivative with respect to r of this cosine integral, and then this cosine you represent as a difference of two exponentials, and in fact you also expand the denominator into simple fractions and makes integration also from minus to plus infinity, using the fact that you are dealing with an even function of k. You can divide by 2 and extend integration from minus to plus infinity, and then you will have here cosine you write as I kr, and I will write it as a sum of two terms. Another will be minus I kr, and expand k squared plus mu squared in terms of, I will write it in this way, k plus ir, k minus ia, and the same is here, k plus ia, k minus ia, where this variable a is simply coincident with our mu. And what is mu? Mu is mc explicitly over h bar. You remember, this is effective expression we have for this mu. In fact, we know that mu coincides, although usually when in the natural units h bar in c is equal to 1, so mu is just m in this system of units. But in fact, if you count physical dimensions of this quantity mc of h bar, you know that what is written down here is a quantity with an inverse, with a dimension of the inverse length, and this is something which we call Compton wavelength of a particle with mass mu. So inverse Compton wavelengths, inverse Compton wave length of a particle of mass m, of a particle of mass m. Very good. So this is the integral we have to compute, and then you see, so the integral is over the real line, but you can close the contour in the complex plane, and in particular for the first integral, exponential I kr, you have to close it in the upper half plane, upper half plane, and for the second integral you close it in the lower half plane. And then you see which poles you have in the upper and the lower half plane, and use the residue theorem. So you compute residue, at the corresponding pole. So in particular, in the upper half plane here, you will have a pole at k is equal to IA. In the lower half plane, you will have a pole at k equals to minus IA, where A is the same as this parameter mu. And therefore, the integral reduces to 1 over 4 d over dr. And I'm writing the result of this integration, 2 pi I, as usual, from Cauchy formula, exponential minus AR divided by 2IA. So this is a residue at this pole, minus what is then 2 pi I exponential, again the same thing, minus AR, and divided by minus 2IA. This is how these residues will look like. And then, what then? Then we see that this is simplified to the following expression, minus pi. So 2's cancel here, 2's cancel here. Pi will be left over, I will be cancelled also. A gets out, and then these two terms double, so you will get 2A in the denominator, d over dr, d over dr, applied to exponential minus AR. You can differentiate, and so what you get here is an minus pi divided by 2A. Well, minus A gets out, exponential minus AR, and so A is cancel, minus cancel, so pi over 2 exponential minus AR. And I will write this then in terms of Compton wavelengths. I will write it as exponential minus r divided by lambda, from where you actually see that what you have as an exponent is correct dimensionless expression. So radius, length of radius vector between the points x1 and x2 divided by the Compton wavelengths. And now we can return to our formula and simply substitute this value of IR in the integral we wanted to compute, and we wanted to compute this quantity here. So let's return to this expression and substitute our result for this integral, and we end up with the following potential. Potential between two static sources mediated by the scalar field phi is given by minus 1 over 4 pi q squared h bar c divided by r exponential minus r divided by lambda. And so this is potential between two equally charged static sources is called Yukawa potential. Yukawa potential. So we derived the formula for the Yukawa potential. In particular, from this explicit expression, what do we see? First of all, we observe a very interesting thing is that this potential appears to be negative, right? So explicitly you see this minus sign in there. For equal charges, q squares enters into this formula, and so changing q to minus q produce the same expression, q squared, as soon as your sources have the same charge, you have this potential with a minus sign. And this potential with a minus sign actually means that the force you are dealing with here is an attractive force. So attraction. Attraction, because you see having a smaller distance between the particles, smaller and smaller, so decreasing R, you will be decreasing the potential, because then it will be having more and more negative values, smaller and smaller energy, in other words, which means that for two sources, it's preferable to approach each other to diminish the energy. So diminishing the energy corresponds, therefore, in this case, to the desire of particles to be closer to each other. In other words, you deal with attractive force, attraction. The second thing which you see is that there is this exponential which dumps the potential when R becomes sufficiently large, in particular becoming bigger than the wavelengths of the particles. Potential shows exponential decay. So potential goes to zero very fast, actually exponentially, with the distance increasing. Yeah, so this is because of this term. And on the top of that, you also see that the interaction range set up by this exponential does depend on the Compton wavelengths. It's governed by this effective length, which is in our case turns out to be Compton wavelengths. This also shows why people call the Green's function propagator, because the propagator propagates interaction from the source, from one source to the other source, or if you wish, from a source to a test particle. It propagates interaction represented by this field phi. And that's why this Green's function is called a propagator, because we see the result of this propagation in the appearance of the force, actual force between particles. So what we do here is a very physical calculation, which shows explicitly what happens if you have two particles inside a space filled with a scalar field phi. What happens is that these particles fill this field, and because of interacting with this field, they start to attract.
Professor,
Yeah.
Can you tell this again, that if our field is a real scalar field, then how means charge is coming into picture here?
Now, charge here is understood as a measure of a strength of our source. It's a strength of our source. So Q here represents how strong our source is. It's this Q standing here. It's Q in front of J1. J1. Okay.
So it doesn't has to be some electromagnetic source. It can be any source, but with
It
this
can be.
expression.
I mean, this of course, this computation can be repeated for electromagnetism, of course, and this is something important. This is something which we'll probably also do at a certain point, to repeat this computation where we have, instead of a scalar field, a mediation by electromagnetic field.
Oh, for example, now we don't have an electromagnetic field, so
We don't have electromagnetic field, but we can still talk about charge. It's a charge with respect to this phi. It's a charge with respect to this field phi. So showing a strength of interacting, or basically a strength of a source which produces our field phi.
doesn't it like means it shows that it is compulsory you have to instill an electromagnetic field here? because of this charge.
Sorry, say it again. Yeah,
Doesn't
it's
it?
very similar to
Yeah.
what you would have with electromagnetic field. Very similar. And we will do this computation with electromagnetic field. The difference between electromagnetic field and scalar field is, of course, the spin. Here we deal with a scalar field, and this is a field of spin 0, while electromagnetic field has a spin 1. And we see that it leads to a drastic difference in the potential. You will see that in the case of two equal charges mediated by electromagnetic field, the potential will appear to be positive rather than negative. So while scalar field tends particles to attract, electromagnetic field, as you know very well, for equal charges will lead to repulsion. And that is essential difference which you will see there. Otherwise, computations will be very similar. The difference is, of course, in the initial point, namely in the Lagrangian, in the action you pick up for electromagnetic field and the one you pick up for a scalar field, because these are fields of different spin. You see?
For example, now instead, like we have a gravitational field interacting with scalar field, so still we have to use this VR, this Q square is this expression.
Yes, you can. Yes, absolutely. You can do the same computation with for the case of a gravitational field, spin 2, and again, as in spin 0, you will find attractive force. And again, it's related to the nature of the action which you will write for spin 2 particle. It's all the time, it's the same computation. You pick up two static sources, like I'm writing down here. You fix them to be, say, J1 and J2, and then you take Lagrangian for your field of a given spin, say 0, 1, or 2, or even more, does not matter. And then you compute the contribution to the energy, interaction energy produced by interacting of your test with a field. And field itself is considered as to produced by a source, as coming from the source. And so this is the way how people compute the potential. This is the way you can compute the potential between two static quarks also in QCD, in quantum chromodynamics. You see, it's a one and the same procedure. So the procedure which I'm showing you here is quite universal. And doing this procedure, let me just say, let me just disclose the truth, is that what you will find out is that fields of even spin mediating interactions between two such static sources will lead always to attraction, while fields of odd spin, so 1, 3, and so on, whatever, will lead to repulsive interaction, provided your sources are considered to have the one and the same charge.
Well, now if the source is like fermionic field, then
Fermionic field, I think you cannot. It's a different story, because fermions are themselves are particles, so you need to mediate them, mediator of integer spin, for instance, by electromagnetism. So they are rather considered as themselves as particles, not as mediators of something.
oh, so you have to add some other extra term with cross interaction.
Right. So say you take fermions and you put your fermions in electromagnetic field. You couple your fermions to electromagnetic field. We consider this situation very soon. And then you can repeat this computation and then see what happens.
Okay. Yes.
Because interaction of fermions, then you are in the, so to speak, realm of quantum electrodynamics, where you have particles, electrons and positrons, and you have a field which mediates interactions between these particles, namely electromagnetic field. Then you are having quantum electrodynamics. But if you neglect the fact that your fermions have spin, if you just neglect the thing, you can say that then your fermions are just particles for which you also like the same thing, delta like source, so point like source. And you have first particle with point like source, and the second particle another point like source, and you do absolutely the same computation, except now mediator will be electromagnetic field.
Yes.
That's
And
the only difference. Yeah.
there you have to like couple the scalar field with the Dirac field, right?
Yeah. So in that case, you have a Dirac field, but you have to mediate the interactions by electromagnetic field, and so electromagnetic field then is an analog of our scalar field here.
Yes. Okay.
Mm-hmm.
Sir, sorry, I have a very stupid question. Can we use the Yukawa potential to explain the Casimir force?
Yes, in fact, you see, the point is that Yukawa potential is a short-range potential because of the presence of this exponential here. On the other hand, you also see the following things, that when lambda tends to infinity, which essentially means, if you remember what lambda is, so lambda is 1 over lambda is mass mc divided by h bar. So lambda to infinity means mass to 0, right? Lambda to infinity corresponds to having mass to 0. So in this case, you have a massless field, massless scalar field instead of massive scalar field. And then you see that your potential between two static sources actually becomes a Coulomb potential. It tends to Coulomb. So in this case, lambda to infinity or mass to 0, you can actually see that V on R becomes minus 1 over 4 pi Q squared H bar C divided by R. So this is Coulomb potential. And so in a way, when you have non-trivial mass, the Coulomb potential in a way gets screened and becomes short range because of presence of this exponential. And in the mid 1930s, Yukawa he was trying to understand the origin of the strong force, which holds together protons and neutrons in the nuclears. So you know that nuclears consist of protons and neutrons, and it was also known that the force acting between these protons and neutrons inside nuclear is a short range. It's very short range. And he made this ingenious conjecture that this strong force was mediated by particle, something similar to photon. Like photon in electrodynamics mediates interactions between electrons and positrons. He said, okay, let's assume that something similar takes place inside our nucleus, and there is a particle, hypothetic particle, which mediates interactions between these protons and neutrons. And assuming that this mediating particle is massive, and following absolutely the same analogy with electromagnetism, then one sees that one needs to add mass to the wave equation. And this produces, as a result, this short-range mediating force between two static sources. So presence of this exponential. So mass, presence of mass results in the appearance of this exponential suppression. In other words, means short-range force. Short-range force because of the mass. And Yukawa actually predicted the existence of a novel type of particle. And from the known data on the range of nuclear forces, he was actually able to predict with quite a good accuracy the mass of this particle. So if you know the range of the strong force, which you can actually do experimentally, then you can deduce lambda, or equivalently, you can find what the mass of this particle should be. No, Compton wavelength is the same as the mass. And indeed, later, this particle called pi meson, or sometimes people call it simply pion, was discovered in cosmic rays. And it also appeared in later in these cyclotron experiments, precisely where it was predicted by Yukawa, precisely in the same range. Although, of course, today we know that, first of all, there are several types of mesons. So we also know that mesons are not elementary themselves, but rather they are composite particles made of the quark and its antiquark. Nevertheless, Yukawa's theory made a very right qualitative picture, and it also, in a way, paved the development of what we call today QCD, quantum chromodynamics. The theory where the fundamental objects are not mesons, protons and neutrons, but rather quarks. Nevertheless, as I'm saying, that was a very important step towards development of QCD by assuming the nature of strong force as arising from a massive particle with zero spin. And this is basically what I wanted to tell you about Yukawa force today. Okay.
Okay,
An
thank you, sir.
interesting story, right?
Yeah, yes.
Yeah, very interesting story. So this computation, which I did today, you have to have in mind that as a general computation, you can apply to a mediator field of any spin. And the very similar computation takes place also for electromagnetism, where you will see instead of minus sign, plus sign in the potential, and therefore repulsive force instead of attraction. In that case, particles, would it be here plus instead of minus, then for particles, it is more preferable to take large distance between them in order to decrease the energy, because then energy is positive and it will be decreasing when R will tend to infinity. You see it from. So sign is very important. You see it from this formula. Sign here is very important, and sign, of course, eventually comes from the equations of motion. Equations of motion are, of course, induced by the type of action you have chosen to describe a particle of a given spin. And as a result, it leads to these physical consequences of as attraction or repulsion. Okay, so now I think I finish with the Yukawa force, and we are going to a new chapter in our quantum field story, namely to the Dirac equation. So Dirac equation. It's a new and very interesting story called Dirac equation. So in 1928, Dirac discovered his relativistic equation, trying to overcome these difficulties with negative probability densities of the Klein-Gordon equation. You remember, we have discussed that Schrödinger already made this attempt before to write down relativistic quantum mechanics by taking just on-shell condition, dispersion relation relating energy and momentum of relativistic particle, transform this condition in the language of operators by replacing momentum and energy with the corresponding operators, shifts in space and shifts in time, and writing down, in fact, the Klein-Gordon equation that was later, of course, rediscovered many times by Klein, Gordon, Fock, and many others. But as we have seen, the problem to treat this equation as a relativistic equation for a wave function phi, it has difficulties with probabilistic interpretation because equation of the second order, and that allows you to arbitrarily fix initial conditions and initial velocities, and that leads to the appearance of negative probability densities. Now, the reasoning which led Dirac to his equation was essentially the following. So first of all, we wish to prevent the occurrence of negative probability densities. And this means that we should avoid time derivatives in the formula for the probability density. For ρ, we should not have have time derivative dt. The wave equation must therefore not contain time derivatives higher than the first order. So if you would have the wave equation, just like in the usual quantum mechanics of the second order in time, no Schrödinger equation, it's the equation which is first order in time, I h bar d over dt, psi is equal to h psi. So standard Schrödinger equation contains time derivative of the first order, while as we discussed, Klein-Gordon equation contains a second order derivative. So Dirac thought that, well, if you want ρ to be good, to have a good probabilistic interpretation, where ρ is a probability density for the corresponding wave function, then wave function must satisfy the first equation, which contains only first derivative d over dt, and it should be looking in this way rather similar to the usual Schrödinger equation containing first order derivative in time. On the other hand, if you want relativistic covariance, then it requires that the spatial and time components, in particular spatial derivatives and the time derivative, must be treated on equal footing. So d over dt and derivative d over dx must be on equal footing. Because in the standard Schrödinger equation of quantum mechanics, this is not the case. While you have d over dt first derivative, typically your Hamiltonian here contains second derivative, right? Something like this, d over dx squared. And so that immediately shows that you are dealing with non-relativistic quantum mechanics, because relativism requires that you can convert t to x and x to t by means of linear Lorentz transformations. And it is impossible to have this if your derivatives in your equation have a different order. That it's simply impossible to relate them. Now, also, one needs linearity to have a superposition principle like you have in quantum mechanics. So equation must be linear. So, okay, let me put all these points as arguments which led Dirac to this equation. So linearity of equation on psi. Just like in the usual quantum mechanics, you have a superposition principle because linearity means that if you have two solutions, then their sum will be also a solution. So superposition principle then will be working. And the last important point is, of course, since you are describing relativistic particle, the relativistic particle must still satisfy the standard on-shell condition for relativistic particles. So E squared plus E squared must be equal to, for this particle, to P squared C squared plus M squared C4. Relativistic dispersion relation must be satisfied. And if you wish, then for psi, that would mean that psi still must satisfy the second order Klein-Gordon equation. Plus mc over h bar squared, if you write it explicitly, acting on psi must be equal to 0, because this equation then produce for us this relativistic dispersion relation that we have seen exactly for the case of a scalar field. When we take, say, psi, write it in terms of Fourier, plug in this equation, and then solution of this equation leads, it's exactly equivalent to this dispersion relation here. Quite a number of conditions, and at first sight you see that it's just impossible to invent something which would satisfy all these, say, 4 requirements. But that was Dirac. So he said the following: okay, so let's try to write down something which would be linear for psi and contains derivatives of the first order. So what then I could write? I could write I h bar d psi over dt. So beginning is the same as in Schrödinger equation. On the right-hand side, all what I can do is the linear combination of first-order derivatives, alpha 1 d psi over dx1 plus alpha 2 d psi over dx2 plus alpha 3 d psi over dx3. Spatial derivatives. No, and then for the later, I will put just overall coefficient, which is needed for my purposes. It's not essential, but to have proper normalizations, physical normalizations of all these quantities, I will put here h bar c divided by I. No, maybe then you can always add a term with psi itself. So adding something which would contain then what we call mass. Beta mc squared, again, this is convenient, for me, convenient normalization, and then a term with psi. Okay, so you write something like this. Equation contains only first derivatives. But then if you think about it, you immediately come to the conclusion that alphas here, these coefficients, cannot be just the usual numbers. Because if they are usual numbers, which you fix to certain values, say 5, 3, 7, then this equation is not even invariant with respect to usual 3-dimensional rotations. Because 3-dimensional rotations will act on coordinates x1, x2, and x3, and they will be just then producing change of these coefficients, alpha 1, alpha 2, alpha 3, and then you see that the equation will be immediately destroyed. In this frame, it looks like this. In the other frame, it will be looking different. So he says, okay, if it's not possible for these numbers, for this alpha 1, alpha 2, alpha 3 to be numbers, let them be matrices. Let them be matrices. If they are matrices, then psi cannot be just a scalar. Then psi should be some multi-component object. Psi should be something which would contain many components, psi 1 and so on, psi n, like this. It also cannot be, psi cannot be a scalar also for another reason, because you know from relativistic covariance that probability density, which would be psi star psi, it must be by relativistic invariant to be a zero component of a vector, because you have for ρ the continuity equation, which involves which is written as d rho over dt plus divergence of g is equal to 0. So this would be a vector probability, a vector defining probability density and probability current, and it's a 4 vector. So rho must be a component of a 4 vector. So it means that psi cannot be just a scalar in this case. And indeed, then suggestion is to treat alpha I as matrices, and psi as a column, with a number of components, psi 1 and so psi n. So alpha as matrices, so let's take them as n by n matrices, and n by n matrices, and psi is an n component column consisting of n components. And Dirac called this object psi a spinor. So such psi is a spinor. To distinguish it for a scalar. Now it's a spinor. By the way, if alphas are matrices, then beta is also a matrix. And psi is a column, then beta is a matrix. So then if you want a concise writing for this equation, you can say that you introduce 3 matrices and alpha 1, alpha 2, alpha 3, and matrix beta, and then your equation for psi takes concisely this form: I h bar c d over dt plus I h bar c, now I put everything into one side, alpha I d over dxi minus beta mc squared acting on psi is equal to 0. This is an equation. Now, what about the force requirement? What about the force requirement that we have to see relativistic dispersion relation coming out for psi? This can be seen as follows. So if you have such an equation for an n-component object, what you can do is to act on psi satisfy this equation with the following operator. Let's hit this equation with an operator I h bar d over dt minus I h bar c alpha I d over dxi plus beta mc squared. This is an operator, mc squared. This is an operator. It's a matrix differential operator. No, first of all, it's a differential operator because it contains these derivatives, and it's also a matrix. When I'm writing I h bar d over dt, you should think about this, that in front of this operator, I have just identity matrix, which I'm not writing. It's like identity matrix. Alpha i's are matrices, and the beta is also a matrix. So it's a n by n matrix with components being these differential operators, d over dt and d over dxi. And so what happens when I hit by this operator my equation from the left? So what I will have then is the following. So you have 3 terms here and 3 terms in the original equation. So altogether, you will have 9 terms. And these 9 terms, when you write them explicitly, you will see that 4 terms cancel out. And the remaining terms, 1, 2, 3, 4, 5, 6, 9 terms. Okay, so you will do some combination. Okay, so let me write down what you will get. You will get minus h squared, second derivative over time. Then you will get plus h bar squared c squared, alpha I, alpha j, plus alpha j, alpha I. I will tell you why it is written in this way. Second derivative of psi with respect to dxi, dxj. You see, these 2 derivatives acting on psi commute. You can write d over dxi, d over dxj, or you can write other way around, d over dxj, d over dxi. And so this expression is symmetric in ij, which actually allows you to symmetrize the product of these matrices, by means of which this expression is multiplied, by which this expression is multiplied. Okay? So alphas are symmetrized. Then you will get a term IH bar MC cubed. You get alpha I beta plus beta alpha I. D psi over dxi, term with the first derivative. And finally, you will get term without derivatives. So mc squared squared beta squared psi. And this is all equal to 0. So this equation, which we have obtained now, is a consequence of this equation. So we assume that psi satisfies this linear equation. And if it satisfies this linear equation, then as a consequence, it must satisfy this equation here, which is now second order equation because it contains second order derivatives, second order derivative in time, second order derivative in excess. No, it also contains the first derivative and the psi, term without derivative, term without derivative. Now, if you multiply this equation by, this is straightforward application of this operator to the equation. You can check it. You have 9 terms when you multiply. Then 4 terms cancel. 5 terms will be left over. These 5 terms is this term. These 2 more, 3, 4, and the 5th term I write in a symmetric way within this ing by symmetrizing with respect to I and j. The other 4 terms which will be there are cancelled. Okay, so if you multiply this equation with minus 1 divided by h bar squared c squared, then this equation takes the following suggestive form. 1 over c squared, second derivative of psi dt squared, minus alpha I alpha j plus alpha j alpha I, divided by 2. Second derivative dxi dxj minus I mc over h bar alpha I beta plus beta alpha I, d psi over dxi, and then plus mc over h bar squared, beta squared psi is equal to 0. And now it's pretty much clear what conditions on these matrices alpha I and beta you have to impose to turn this equation here into the Klein-Gordon equation. You want this now to be exactly the Klein-Gordon equation for each component of psi. Each component of psi must satisfy the Klein-Gordon equation because psi is supposed to describe relativistic particle with a standard dispersion relation. So what do we deduce from here? What we have to impose? You see that you need to impose the following. Alpha I, alpha j plus alpha j, alpha I must be equal to 2 multiplied with delta ij, where I and j run from 1 to 3. Then this will turn simply into second derivative of psi with respect to dxi squared. Then you need to require that alpha I beta plus beta alpha I is equal to 0. Then it will remove this term with the first derivative. It will not be there. No, and finally, you need to require to get the standard Klein-Gordon equation for a particle of mass m, you need to require that beta squared is 1.
So it shouldn't be minus in between?
Sorry?
Shouldn't it be minus in between instead of plus?
In between what? In between alphas?
Yes, alpha, alpha j.
No, this plus comes from symmetrization. Original expression I get is alpha I, alpha j. Then I'm saying that I'm symmetrizing I and j, and symmetrization means plus. Now, plus is very important. Why you would like to have minus? I would like to have plus here. I would like to have plus and replace it by 2 delta ij.
I thought that like means if you define like commutation relation, so that's a
No, this is this is not commutation relation. Exactly, this is not. And I'm not defining anything. I'm just saying I'm computing the result of the action of this operator on my wave function. And then I require that these alphas satisfy such a relation that what I'm getting here turns into the standard Klein-Gordon equation. So I'm not doing anything artificial, and what I'm getting is direct consequence of this mathematics. So these are requirements which Dirac imposed on these matrices to get the standard Klein-Gordon equation. If you get Klein-Gordon equation, then you are guaranteed that any solution of this equation describe for you a psi, which is a n-component column where each component of it satisfies the standard Klein-Gordon equation. You see, then for each psi, an equation you get for psi then is the following: 1 over c squared, second derivative of psi with respect to t, minus dxi squared, plus mc over h bar squared, psi is equal to 0. There are no any more matrices involved. So this equation is valid for each component of psi because there are no matrices. Matrices are disappeared. They all now proportional to coefficients proportional to identity matrix. So therefore, you should think that now this operator, Klein-Gordon operator, is applied to each component of psi. So equation which you get from here is simply d mu plus mu squared acting on psi, which is just Klein-Gordon equation applied to each component of psi, say psi1 up to psi n, you get 0 here. So each component of your multi-component spinner satisfies the standard Klein-Gordon equation, which appear as consequence of this one. So this fundamental equation here. Yeah.
Shouldn't be there some constants multiplied with del mu, because our xi is our means 4 component vector, right? So
Yeah,
you
here,
need, so you need to make it like something like, right? Something this, so as to make it a 4 component form.
Here mu is summed. So mu is here running 0, 1, 2, and 3. When you write it explicitly, you get derivatives with respect to time. This is this term here. And then derivatives with respect to spatial directions. These are these terms here. And then there is a mu squared multiplied by psi. This is this term here. So I'm not quite.
I want to say that if it defines in Klein-Gordon equation only, then Dirac equation.
Yeah.
So means how it's different, means the expression should be like something different, right? Klein-Gordon equation.
What do you mean? Klein-Gordon equation is an equation d mu plus mass mc over h bar squared acting on whatever you want, phi or psi is equal to 0. So this is Klein-Gordon.
Means it's exactly similar to that.
It's not similar. It is a Klein-Gordon equation. Why you say similar? It is a Klein-Gordon equation. This is what we call Klein-Gordon equation.
No, but it's a 4 component vector, right?
It is a multi-component vector. For the moment, we don't know how many components it should have. We assume that it has n. And then any component of it satisfies Klein-Gordon equation. That's what I mean by this.
Okay, the form you are telling about only.
Yeah.
Okay, yeah.
So you have this equation, but you still remember that psi is column. And so this means that this Klein-Gordon operator acts on each component of this column. And so the result of this action must be 0 for each component of this column. So each component satisfies Klein-Gordon equation, mc over h bar squared, like this, acting on psi I is equal to 0, where I is running from 1 to n. So relativistic dispersion relation, therefore, is inherited by each of these components from psi 1 to psi n. Okay?
Okay, sir.
Okay, very good. So what do you see? I'll make one comment and maybe finish with this. So what do you see from these relations? The immediate thing which you see is that if you take indices I and j to be equal in this expression, so then you get alpha I plus alpha I. Then it's equal to 2. So in other words, 2 alpha I squared is equal to 2. So from here you deduce that alpha I squared, square of any of these matrices, is equal to 1. So I is, as I said, running 1, 2, and 3. So any of this matrix squares to 1, and beta also squares to 1. And this is directly comes from the condition we have to impose on beta. So all the matrices square to 1. That's our first consequences for these matrices. Alpha I squared is equal to 1 is equal to beta. When I say 1, I mean identity matrix. because alphas and betas are matrices, so identity matrix is what do they square to. This means in turn that all eigenvalues of these matrices alpha I and beta can be only plus minus 1. So eigenvalues of any of these matrices is plus 1 or minus 1. Second important observation is that all these matrices, they have zero trace. How do you see this? That is, for alpha i's, you see it from the condition alpha I beta plus beta alpha I. Just a second, I will write it like this. Alpha I plus beta alpha I is equal to 0, from where it follows. So beta is invertible because beta squared is 1. And so I can invert and write alpha I equals to minus beta alpha I beta. And now I take a trace. Trace of alpha I is minus trace beta alpha I beta. Trace is cyclic. So under the trace, I can put this beta to another beta cyclically. So I get beta squared, but beta squared is 1, identity matrix, and I get minus trace alpha I. So trace alpha I is equal to itself with minus sign, which is only possible if trace alpha I is equal to 0. Right? Analogously, trace beta is equal to trace, take any alpha, and then since alpha I squared is 1, I can write it as trace alpha I squared with beta, because this is 1. This is identity matrix. Then I write this as minus trace, no, first as plus trace alpha I beta alpha I, bicyclic property of the trace. And then this is from this relation here. This is nothing as minus trace of beta. So again, from here you see that alpha I beta alpha I is minus beta, and this is what I'm using here. So I will get minus trace beta. So trace of beta is equal to itself with a minus sign, from where it follows the trace of beta is 0. So trace of alpha I equals to 0 equals to trace of beta. It means that the number of plus eigenvalues must be the same as number of minus eigenvalues. So number of plus eigenvalues must be equal to the number of minus eigenvalues in order for the trace to be 0. So eigenvalues are plus minus 1, but they are, the numbers of these eigenvalues must be such that the trace should be equal to 0. And therefore, this is only possible when n, the dimension of our multi-component spinner is integer. Is even. Number n must be even. Yeah.
So from here we can also say that our means here matrices should be special orthogonal, right?
No, we cannot conclude that. We are saying just that the square of this matrices is 1.
If the eigenvalues are plus minus 1, from that sake.
No, eigenvalues, these matrices generically they are complex. They are complex matrices, and we will develop a bit later on what are they explicitly. Eigenvalues, yes, eigenvalues are plus minus 1, but this is just a consequence of the fact that squares of these matrices is equal to identity matrix. That's the only thing which we see here. We don't know how these matrices behave themselves with respect to transposition. That we did not find out yet. Right? We don't know how they behave with respect to transposition, so we cannot say anything about orthogonality properties of these matrices. So for the moment, this is what we have. And so, but the dimension of these matrices must be necessarily even. Then the dimensions must be necessarily even. So I think with this, I will probably stop here because our time is over. But the next time I will continue with this and develop this representation theory of these matrices, which is related to the construction of the Dirac equation. I will do it in detail. But for today, that is all. If you would like to ask me some questions, please go ahead. No questions for the moment, right? Okay, then I wish you a pleasant day, and we will meet and hear each other next Friday.